Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Now that we have some initial data for a mesh, we can go ahead and write the processing part of the geometry pipeline. In this video, I'm going to write a function that determines what the normal vector should be at each vertex. Using this function and the smoothing angle, we can define soft edges and hard edges for our mesh geometry. So we need to implement these two methods now. Here in geometry header, I'm going to add those function declarations. And then I'm going to add a CPP file that we can use to put the implementation of these two functions in there. So what process scene does is just go through our lots, our meshes, and process those. Let me tell you more about what this process scene actually does. So right now the processing stage consists of two parts. The first part is to determine which edges should be soft edge and which ones should be hard edge. And as you can see here, depending on what smoothing angle we give the processing stage, it will create soft planes for us or hard edges. And the idea behind this is that we have a position vertex, as you can see here in pink, and that represents just one point in the 3D space. And this point is referred by multiple triangles. If each triangle has a different normal, here in green, you can see that different points can have different normals. And what we do by this smoothing angle is to tell the processing stage whether to split this position vertex into two or keep it one and then take the average of the two normals. In the first case, when we split the position vertex into two, then we effectively have two separate triangles with different normals, and that results in a hard edge. And when we average the normals and keep one position vertex and one normal, it will result in a soft edge. So that's the responsibility of the normal processing stage. And we can do the same for the UV coordinates. This same corner of this cube, point A, will be mapped to different points on the UV plane. And when that happens, we also need to split the position vertices in two. And later when we have tangents, we need to do the same. And there are more stages in processing that we will be doing later when we have like an importer for our 3D models. Then it will be justified to do full processing on our vertices. But right now, these two will be all we need to do to get something out of the geometry tool chain. So as you can see here, we need to basically write two functions that do this for us. First, let's implement this process vertices function. First, we check if the number of indices that we have is a multiple of 3 because we need a triangulated mesh to process. Next, if we don't have any normals or the settings tell us that we need to calculate the normals explicitly, we calculate the normals. Then we process the normals, which will split the normals and position vertices for hard edges and average the normals for soft edges. And then, of course, we need to split the vertices for different UV coordinates. And the last step for now is just to pack the vertices. And by this, I mean packing the vertices in a format that can be understood by the shaders that we will be writing for our rendering engine. So everything is packed tight and nicely together. Let's start by implementing recalculate normals. Calculating normals is pretty straightforward. We can construct two vectors from the two edges of each triangle, and then the cross product of those two edges is the normal of that triangle. So construct two vectors, take the cross product of them, and then you get the normal. And repeat that for each triangle in the mesh. So here we resize the array of normals to the number of indices. And that's for the following reason. Our processing stages have some preconditions. As we discussed before, vertex processor conditions are as follows. The vertex positions should be unique, except when we want to coerce hard edges. Because the processing stage doesn't merge any position vertices, it only splits them. When we have non-unique position vertices, no matter what smoothing angle we give the processing stage, it will always result in a hard edge. But if we really want to control the hardness of the edges by the smoothing angle, we need to give it unique position vertices. So for example, if you look at the top plane of this cube, you can see that, well, the cube as a whole has 8 unique position points, and we can create triangles for those. And if you look at the top plane, you see the triangle 1, 4, 2, because we are winding counterclockwise, so that our normal in a right-handed coordinate system will point upwards. And the second triangle is 2, 4, and 3. And for each of these triangles, we need to provide 3 normals. So for the first triangle, we have normal 1, 2, and 3, and normal 4, 5, 6 for the second. And the same thing holds for the UV coordinates as well. And that's why we are going to calculate the normal at each index instead of have a unique normal for each position vertex. Here we go through all triangles and get the indices per triangle. So we increment the value of this counter I. And to calculate the vectors from the edges, I'm just going to use the DirectX math library. Here I load the position for each index in one of these XM vectors, which is basically a SIMD register. And then I can subtract these positions from each other to form 2 vectors. And next I can calculate the cross product of these 2 vectors to get the normal. Here we calculate the cross product of these two vectors and then we normalize them. And finally, we store the result in the normals at this index. And because we have, again, 3 normals per triangle, we need to subtract 1 and 2 from this index to get to all 3 vertices of that triangle. And this is all we have to do to calculate the normals for all triangles in the mesh. Next is processing the normals, and that was the process of splitting the position vertices to have hard and soft edges. So let me explain a bit more about this smoothing angle. With the smoothing angle, we just tell this function which angles should be considered soft and which angles should be considered hard. So when we set the smoothing angle to 120, for example, we need to account for each direction for the angles. So we have reflex angles and obtuse angles. In this case, this one is a reflex angle and this one is an obtuse angle. But this could also be an acute angle, which is less than 90 degrees. But we can account for all of this by just one smoothing angle, because if you look at the cosines of these angles, you can see that anything that's less than 120 degrees, so if this angle would be less, then we should consider those a hard edge. And anything that's bigger or larger, we should consider as a soft edge. And if we calculate the cosine of those angles, this relationship is flipped. So if this angle between the normals is less than the cosine of alpha, then we should consider this edge to be soft edge. And if it's larger than the cosine of alpha, which is the cosine of smoothing angle, then we should consider this edge to be a hard edge. And I'm using the cosines instead of comparing the angles directly, because using cosines accounts for both types of angles, either reflex angles or obtuse angles. And on the other hand, calculating this theta, which is the angle between normals, is faster if we just get the cosine of this theta, because we are going to take the dot product of these two normals, and the dot product of the two normals is proportional to the cosine of the angle between the two normals. And that's why I'm just going to use the cosine of the smoothing angle instead of smoothing angle directly. If we set the smoothing angle to 180 degrees, that means that there is nothing that we can do that would result in a soft edge, because anything that would deviate just a little from being perfectly flat would result in a hard edge. So we could skip parts of the calculations if we know that we have only hard edges. So this Boolean is true if absolutely everything is hard edge. And the same holds for soft edges. If anything that is not a close angle, that's just a zero angle, anything other than that will be a soft edge. So in that case, we only have soft edges. Okay, here we are going to generate some intermediate data in our mesh. So we need a new array for the indices that we will be generating, and also something that is more like a vertex data structure that we can convert to the final form of a vertex that we send to the level editor. So going back in geometry, I can add those intermediate data types. Here we have a new data structure that's called a vertex. And a vertex is just the combination of these parts. So after we process everything, then we have one vertex. So one vertex here has tangents, which is a 4-component floating point vector. And again, we'll come back to this later in a later video, but for now we just use these three, which is the position, the normal, and the UV coordinate for this vertex. And all the processing stage does is to generate these vertices. Okay, if we look at this image again, you can see that we need to go through all vertices and see which position is referred to by which triangle, and then we need to check what exactly the normal vector is on that index for that triangle. And that means that we need to pick one position and then go through the list of indices to see where it's referred. So basically it will come down to a quadratic algorithm, which is rather slow. And to speed up things a bit, I'm going to just loop through the indices once and see which index refers to what vertex position, and just remember that. And that makes calculating this a lot faster. So all this does is go through all the indices and see which index refers to a particular vertex position, and remember that position in the index array. Here you can see what I mean by that. We have the positions and the indices. And for example, here, the first position vertex is referred to by the 0th and the 3rd index in the index list. So the index ref will contain 0 and 3 for the first vertex. And so for the second one, it's referred by the indices at position 2, 4, and 7. And 1 and 8 for the third position, and 5, 6, and 9 for the fourth one, and so on. So this makes it easier to figure out what vertex is referenced by what index. Here we go through every index that's referring this vertex at position I and see if the normals at those indices are the same, or they deviate more from each other than the smoothing angle, and in that case we can split these vertices. So we are creating our first vertex, and the index to that vertex is just the size of our vertex array. Right now in the first loop, or a first iteration, it's 0. And this vertex is referred by an index at this position. So we should put the index of this vertex in the indices array at this position. I hope that's a bit clear. If you really stop and think about it for like 5 minutes, then it becomes clear if it's not already, but it can seem a bit difficult to wrap your head around these double indices, but once you get it, and it will be okay. So we place one vertex in this vertices array, and this emplaceBack function will return a reference to that newly created vertex. And this index refers to the vertex that we are processing right now, and it has this position, which we will use and put it in the new vertex. Now comes the calculation of whether we are having a hard edge or a soft edge, or in other words, should we average all the normals for this vertex or not. First, we take the first normal for this position. If our mesh is hard edge and we can do nothing to create a soft edge, we just skip this whole calculation, and all we do is just split all these positions to the same number of indices. So we have 3 positions for each triangle. And if not, we do this calculation here, and after that we have a normal in our vertex, which we then will normalize and store here. To calculate the average of normals, you just add all the vectors and then normalize them. And then that way you get the average of all normal vectors. Okay, so here we have the first reference to this vertex position. And now we are going to consider the following references to the same position vertex and see if their normals are different. So as I explained before, we are going to calculate the angles between the normals. And here we have a value that represents the cosine of that angle. And well, we got the first normal loaded here, and we just picked the next one, which is n2. And again, if all angles are soft angles, then we skip this calculation or the part of it. And otherwise, we need to calculate the cosine of the angle between these two vectors. To calculate the cosine of the angle between two vectors, we need to take the dot product of those vectors and then divide by the product of their lengths. The reciprocal length is just 1 divided by the length of n1. And we don't multiply by the reciprocal length of n2 because n2 is already normalized and the length of it is 1. So we save a little bit of work there. But since we are going to modify the value of n1, then we know that n1 is not normalized anymore, and therefore we need to account for its length here. Now that we know the cosine of the angle between these two normals, we can check if the normals should be added together or split. If we are having only soft edges, we just average all normals anyway, and we didn't calculate this. But if we don't have all soft edges, then we check for this condition, which we talked about earlier. And if this cosine value is larger than the cosine of the smoothing angle, then we should consider this a soft edge, and therefore we should average the normals. And we do that by just adding the normals together. Since these two indices now refer to the same vertex, because that vertex has the same position and also the same normal, the index values should be the same. And we also remove this reference from the array of references. And well, the number of references goes down by 1. And we also need to decrement this loop index because we just removed one element from the references, which will shift all the items in the array down. So we should also decrement this index. And this function just takes care of calculating the normals for the indices. Next time, I'm going to write a function that does the same kind of processing for UVs, and also I'll pack the resulting vertices in a compact format for upload to the GPU. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!